Hello everyone, my name is Ke Chen. I'm a doctoral candidate from the Technical University of Munich. It's my great pleasure to present my work, Real-Time Contact State Estimation in Shape Control of Deformable Linear Objects under Small Environment Constraints to all of you. Environment constraints such as the three fixtures shown below have been widely utilized in the shape control process of deformable linear objects. To enhance the robustness, reliable contact state estimation between the DO and fixtures are crucial. Especially we find that due to their own deformation, the clip-like fixtures introduce a unique and dynamic contact process, where the contact force undergoes multiple stages of change. This motivated us to propose an accurate, real-time contact estimation approach that can be used across various settings. We start with the formulation of the clip fixing process as a sequence of manipulation primitives. We also observed from our prior work that some problems can happen at different stages of this process. We noticed that these anomalies have different contact patterns and thus can be detected and avoided by accurate contact estimation. Inspired by the definition of stiffness, we then define an indicator for describing the contact change, the rho C, as a rate of change of the resulting contact force to the feed-forward force. In the example below, we can see a case where rho C detects both contact detachment and re-establishment as it falls outside the confidence interval, but the vanilla contact force change rate fails to do so. Then we define another indicator rho E to detect whether there is a solid contact between the DO and the clip established. Based on these two indicators, the ideal clip fixing process can be characterized by the contact force pattern. Finally, we integrate the contact estimation method into the shape control process to form an adaptive framework, which could detect and correct anomalies automatically. Now I would like to show some real-world experiments and results. We firstly compared the performance of our contact change indicator to two other intuitive indicators across various force rising patterns, positions, cable sizes, and clip shapes. The video, together with the statistics, showed that the proposed contact estimation preserves the most robust performance across various settings. Last but not least, we evaluate the performance of the enhanced shape control process. Here we see two front-end manipulators attack the cable onto four clip fixtures. When the clipping attempt fails, our framework can detect the failure from contact estimation, adjust the parameter, and give another attempt until a success.